Today is all about word problems. As soon as you get back from spring break, maybe even this week, you started on optimization problems. And the hardest part of those is taking that question and deciphering it and making it into an equation, a constraint, and an objective function. So this session is all about deciphering those problems and making them into the math problem that you can solve. So I started with some that are just writing a function to represent a geometric relationship. And I think you have one kind of like number 1 on your lab for optimization. Determine a function to represent the distance from the point to the parabola. And in calculus, you would want to be minimizing that distance. So that requires the distance formula. And just in case you don't remember that, if you want the distance from point x1, y1 to point x2, y2, distance is equal to the square root of the change in the x's squared plus the change in the y's squared. And that comes from the Pythagorean theorem. You just draw a right triangle that connects the dots, and that's the distance between them. So if we want to represent the distance from a point to 1 to the parabola, y equals x squared minus 2x plus 3. This is one that, drawing a picture is kind of optional. I went ahead and put it into Desmos, but of course on test day, you won't have Desmos. If you wanted to sketch yourself a picture, well, the 2, 1 is easy. You know where x squared minus 2x plus 3 crosses the y-axis. 1, 2, 3. You can go to your polysolve button, and you have to press second to get to polysolve. Put your quadratic in there. So 1, clear out the old stuff, -2. Clear out the old stuff, 3. You know that it's an upward facing parabola. And now if you keep pressing enter in here, it writes it in vertex form for you. So you can read off what the vertex of that parabola is. So we know it crosses the axis here at 3, and its vertex is at HK. So 1, 2. 1, 2, right here. So we sketch a pretty good graph, pretty good estimate of what that looks like just using our calculator, not even needing Desmos. Yeah, that's so bad. I can't stand it. I have to make it look a little better. So now the distance from my point, I'm going to call my point x2. I would have 2 minus x squared plus 1 minus y squared. But we want a function that only has one variable in it. So I'm going to replace y with x squared minus 2x plus 3. If all you were asked for was a function, then you could be done. That is a perfectly good function. I did some simplifying on it, which is just algebra. Questions about that one?
Yeah, I don't really have problems with like polynomial functions, like the radicals and stuff like that are where I really have trouble, and like cosine and sine, the trigonometry ones.
Okay, good. So hopefully this next problem will be pretty easy for you too. Determine a function to represent the area of a square that is inscribed in I left out the word circle, with radius 10 that is centered at the origin. So first I'm going to sketch a little graph of that. Because again, on test day, you won't have Desmos. So there is my perfectly round circle with radius 10. And I want to represent the area of a square that is inscribed in there. And let's see. Yeah, that should be a rectangle. We want the area of a rectangle because there's only one square that we can inscribe in there. There's lots of rectangles. So let's determine a function to represent the area of a rectangle. In a circle with radius 10 centered at the origin. Perfect. Okay, so hopefully you remember from your pre-calculus class that the formula for a circle centered at the origin with radius 10 is x squared plus y squared equals r squared. And since the radius is 10, that's 10 squared. So x squared plus y squared is equal to 100. And now we're looking at this rectangle in here. The width of the rectangle is the distance from negative x to x. And the height of the rectangle is the distance from negative y to y. So area is going to be 2 times x times 2 times y. So that's 4xy. But again, we need a function that only has one variable in it. Since x squared plus y squared is 100, y squared is 100 minus x squared. So y is plus or minus the square root of 100 minus x squared. And since we're talking about lengths and distances, we'll go with the positive one. So area is equal to 4x times the square root of 100 minus x squared. Easy enough. There's the pretty picture. Optimization problems also often have volumes and surface areas, and you want to maximize volumes and you want to minimize surface areas because you want to get as much stuff in the box as you can, but you want to spend as little as you can to make the box. So you're either given a volume and you need to figure out a surface area, or you're given a surface area and you need to figure out a volume. So let's determine a function to represent the surface area of a box with a square base that has volume 25 cubic meters. You're expected to know all these geometry formulas Boxes are easy. The volume is just length times width times height. And since this one is a nice cube with a square base, the sides of the base are exactly the same. It's just the height that's different. And you can name them whatever you want to name them. I like X's and Y's because I'm boring. So my volume for this particular box would be X squared times Y. Then we need a formula for the surface area. Oh, and that volume has to be equal to 25 because that's what we're given. So this would be a constraint in the vernacular of your optimization problems. The surface area, we have to add together the areas of all the sides. Well, the bottom and the top have area X squared. Since the bottom is a square, all of the sides have the same area. It's X times Y. That one's X times Y, X times Y, and X times Y. So we have 4 XYs. Now we go back up here to find a function that we can write Y in terms of X. And since X squared times Y is 25, Y is just 25 over X squared. X squared plus 4X times 25 over X squared. 2X squared. I have an X on top. I have 2 X's on the bottom. So I'm left with just 100 over X. Easy peasy. Again, stop me when you have a question. You're also going to see cylinders. Cans are shaped like cylinders. Anytime you have a 3D prism that has vertical sides, the volume of it is just the area of the base times the height. And since the area of the base of this is just a circle, the volume is pi r squared h. We want to determine the volume, and the surface area is given to us. This time it's 75 square inches. Surface area of that cylinder, well, is kind of like this. You take a rectangle and spin it around. If you undo it, you have the circumference of the cylinder as the width of the rectangle times the height. So for the outsides, it's equal to 2 pi r, the circumference, times the height. And then you have a circle on each end. So 2 times pi r squared. So that's where that comes from. That has to be equal to 75. Volume is pi r squared h. And we want to rewrite this with just one variable in it. So I'm going to take this one, the constraint, and solve for h. So 75 over 2 pi r minus 2 pi r squared over 2 pi r equals h. So So 75 over 2 pi r minus all of that goes away. I'm left with just one r on top to represent h. So my volume is pi r squared times 75 over 2 pi r minus r. And I would want to distribute that and make it look a little nicer. So that pi cancels with that pi. R squared leaves me with 75r sitting on top, 2 sitting down below because the pi canceled, minus pi r cubed. And now when you get to the next step, that's something really easy to take the derivative of. I did post a cheat sheet with all of these equations on them a couple of weeks ago. I will put it in the chat in just a moment for you, and then you can have it. Let's see. I put it out the week before we started with related rates. So let me you start trying to draw a picture that represents practice number 5, and I'll stick that in the chat box for you, that little document. So a lot of these you probably already know. Rectangular prism, circle, right circular cylinder. We do expect you to know the volume of a right circular cone, but I don't really expect you to know the surface area of a right circular cone because that one's pretty complicated. A sphere, and then these were just some other things that are important to know, the Pythagorean theorem and SOHCAHTOA. Yeah, I don't think there's anything else that you need to memorize, any other weird shapes. Mostly we are going to talk about cones, cylinders, and circles and squares. So you're probably in good shape. You won't have to struggle too much to memorize stuff. Okay. So now the even more complicated optimization problems where we have pipelines and lifeguards and people running races. A small resort is situated on an island off a part of the coast of Mexico that has a perfectly straight north-south shoreline, which is very unrealistic, but in math problems, they're always perfect. So first thing you do is read your problem carefully and highlight it or underline important facts, which if you're taking the class seated and you get to take your tests on paper, then you're lucky. You can actually write on the paper and do that. Then you draw a picture if you can. Determine what you're trying to solve for, and usually you find that in the very last line. You determine variables for the important quantities, find a relationship, you solve, and then at the end, always go back and be sure you answered the right question, and always go back and be sure that it's reasonable. If you get a negative number and you're trying to solve for a distance, then you know you did something wrong. So let's see if we can draw a picture of this. We have our shoreline, and there is a small resort on an island that is perfectly straight, and point P is closest to the island, exactly 6 miles across from. So here's my island. It has a palm tree on it. And here is my point P that lives on the shoreline, 6 miles across from the island. And 10 miles south of P is the closest freshwater source. So 10 miles. Here's the water source. I don't have a good picture for a water source. A pipeline is going to be built from the island to the water source by laying pipe underwater in a straight line from an island to a point Q on the shoreline that is 5 miles from the water source. So this is 5 miles. Well, since the whole distance is 10 miles, if that's 5 miles, then this is 5 miles. And then laying pipe on land from Q to the source. It's $400 per mile to lay pipe in the water and $200 per mile to lay pipe on the land. How much will the pipeline cost? So that means our goal is a cost formula. And our cost formula is going to be the cost of the pipe underwater. So we'll call that cost of underwater pipe. Plus the cost of the land pipe. So we have to get from the island to Q, and then from Q to the water source. So this cost is easy. The land pipe is just equal to 5 miles times the cost under land, and it is $200 to lay pipe on the land, so 1,000. Now we need to know the length of Q in order to calculate the cost of the water pipe, the underwater pipe. So luckily we have a right triangle. So x squared plus has to be equal to 6 squared plus 5 squared. So x squared is 36 plus 25. So x squared is 61. So x is the square root of 61. So the cost of the pipe underwater is $400 times the square root of 61. Now your problems will be more interesting because you'll be trying to figure out exactly where along this coastline you should place Q in order to spend the least amount of money on your pipeline. Yes, Pythagorean, exactly. Where do you find that from the O's of the...
So you said you'll have to figure out where Q is. How do you figure out where Q is?
Yeah. So instead of being given, let's see, let me do a little quick sketch here. You'll know how wide the river is. You'll know what this distance from crossing the river, point P, to the water source is. But Q will be variable. So you'll name this side X and this side Z or some other variables. And then this length will be 10 minus X. So then you would have the cost of the land pipe would be $200 times 10 minus X. And then the cost of the underwater pipe would be $400 times Z, and you would need to make a function for Z in terms of X. And again, that's a job for our old pal Pythagoras, because Z squared is equal to 6 squared plus X squared. So Z is equal to the square root of 36 plus X squared. So now you would have a cost function equal to 200 times 10 minus X plus 400 times the square root of 36 plus X squared. So that's the kind of function that you're going to see in your calculus problems. This will be your cost function, and you'll take the derivative of it, you'll set it equal to 0, and then you'll make sure that you have a minimum cost and not a maximum cost, because maximum cost would suck. Okay. And again, at the end, go back and make sure that it's reasonable. If I had come up with a negative answer, then that's not reasonable. All righty, so similar problem. Susie's going to kayak from the island in the example above to a point 7 miles from the water source, and then run the rest of the way. So this one, we wouldn't know where Susie was going to land her kayak. We would have to figure out where she should land her kayak to get there as fast as she possibly could. But right now we're just practicing writing down a formula. So I named the point that Susie lands on the shore Q. This one has a little extra added twist because it's not just a cost that is cost times the number of miles. You have to figure out the time. It's 6 miles wide and 10 miles to the point where she's going, to the water source. She's going to go to a point that is 7 miles from the water source and then run the rest of the way, hopefully not carrying the kayak. She can kayak at 2 miles per hour. So kayak at 2 miles per hour. And she can run at 6 miles per hour. If she leaves at noon, when will she get to the water source? So we are trying to figure out how long will it take her to get there. So we need a time function. So time is going to be equal to her rowing time plus her running time. Now, we don't have distances. We have one distance. We have the 7 miles. We don't know how far she's going to kayak. We can figure that out from Pythagoras again. But we need time, and we're given miles per hour. Well, we go back to the ever popular distance equals rate times time. How far you go is equal to how fast you're going times how long you travel. So time is equal to distance over rate. We know our rates. We can figure out our distances, so we can figure out our times. So time would be equal to the rowing time. So rowing distance over rowing rate plus running distance, and we already know that one, over running rate, which is 6. So all we need is the rowing distance. Which is x squared equals square root of 6 squared plus 3 squared. So x is equal to the square root of 36 plus 9, looks like 45. And yep, about 6.7. So then you can figure out that it takes about 4.5 hours for her to get to that water source. So hopefully she brought some water with her, and she's not going to wait till she gets there. So that's another technique you're going to need to be able to use. That distance is rate times time, so time is equal to distance over rate. You'll need to be able to use that for your optimization problems. Okay, now we are going to go to one of those volume and surface area problems with the added twist of cost put in there. So Aram plans to knit a cylindrical container with no top. So it's just going to be like a little bowl. The yarn he plans to use costs 5 cents per square inch. He wants the radius of the container to be 5 inches and needs it to hold 250 cubic inches. How much will he spend on yarn? So again, your problems will be how can he minimize his yarn cost and have his container hold 250 cubic inches. We need a cost function. And the cost is going to be based on surface area. We need the cost of the surface area of the base. So that would be pi r squared plus the area of these little outside edges of his container, which is 2 pi r h. So it's kind of like that cylinder that we talked about a moment ago with surface area and volume. It's just this one has no top, so you have to read your questions carefully to see whether they have a top or not. Our volume, which is pi r squared h, has to be equal to 250 cubic inches. So in your calculus problems, you won't be given this radius. You will rewrite your cost function, and this is not cost, this is just surface area, because I haven't multiplied it by the 5 cents per cubic inch. But you'll have to rewrite this so that it only has one variable in it. And since this has h's, and you have two terms up here with r's and only one with h's, I would rewrite it with nothing but r's in it. But we don't have to do that. We're just building up to it, so it's going to be the cost times pi r squared plus 2 pi r h. And we know that the radius is going to be 5 inches. We just want to know how high he's going to need to make the sides and then how much he's going to spend on his yarn. So since volume is 250, is pi and our r is 5, 250 over 25 pi is equal to my h. So cost is just 5 cents times pi times 5 squared plus 2 pi times 5 times 250 over 25 pi. And that is multiplied by all that stuff. And you don't need to watch me plug that into a calculator. It's going to cost him about $9 to make this container. Easy enough? Okay. So we have a knitter. Now a chica is going to make a jewelry box. She's going to use walnut that costs 26 cents per square inch for the bottom and sides, and use zebra wood for the top, and that costs 35 cents per square inch. It's going to have a square base and be 3 inches tall. So at that point, I would probably draw a picture. Here's my square base, 3 inches tall. I am not a great artist, but you know, you do what you can. You make it look as good as you can. So there's the pretty picture. So it's 3 inches tall. And this is a square base. Of course it is, even though it doesn't look like a square base. And she has saved up $8.75 for the zebra wood because it's really pretty. My husband does woodwork. And her dad's going to pay for the walnut. What are the dimensions of the largest jewelry box she can make, and what will be the total cost? So this is kind of like a calculus problem, but no, you wouldn't have a definite number for either of them. So she has $8.75 is equal to the area of the top of her box. And the top is going to be a square. So x squared times the cost of zebra wood, and the zebra wood, I looked it up, is 35 cents a square inch. So then we solve that, divide both sides. So x is equal to 5 inches. yes, I planned it that way. So we'd get a nice friendly whole number. So the cost of the box is going to be equal to the cost of the top. We already know that is $8.75. Then we have the bottom here, and the bottom is going to have the same area as the top. So that would be x squared times the cost of walnut, and walnut was 26 inches, 26 cents per square inch. Now we need to know the height. Well, the height was 3 inches, so each of the sides has area 5 times 3. We have 4 of those times 26 cents. Again, your problems, you will be given a volume and you'll have to find the box that is the cheapest. Or you'll be given a surface area and you'll have to find the biggest area. Okay, looks like I have one more here. Because you're probably going to have a Norman window question. Every optimization book I've ever read has a question about a Norman window. I know there's one on your lab. That's a window that has a rectangle with a semicircle on top. So instead of just doing a Norman window, I made a running track. Paolo is planning to build a running track for the neighborhood. He wants it to be in the shape of a rectangle with semicircles on each end, because that's what running tracks look like. The perimeter of the inside of the track is 400 meters. He wants to plant grass inside the running track. The straight sides are 100 meters long. What is the total area inside the running track? So this one I can kind of draw. This is 100 meters. And then we plop half a circle on each end. So that means that the diameter of the circle is equal to the width of the rectangle. Now my goal is to figure out the area of this whole section here. So it's going to be the area of the rectangle plus 2 times the area of these half circles. But if you add 2 semicircles together, you just get a circle. So it's really just the area of a rectangle plus a circle. And the rectangle is going to be 100 meters times the diameter plus the area of a circle is 2 pi times, actually, area is pi times the radius squared. So diameter is twice radius. So if we can figure out what the diameter is, we can figure out what the radius is. Life is good. Those two are buddies. If we have one, we have the other. We do know that the perimeter of the inside of the track is 400 meters. So perimeter equals 400. So if we take 100 plus a diameter plus another 100. Actually, not a diameter. We want to go around here. So it's 100 plus 1/2 of pi times the diameter. So half the circumference of a circle, plus another 100, plus another half of a circle. That has to be equal to 400. So 400 has to be equal to 200 plus pi times the diameter. So 200 has to be equal to pi times the diameter. So 200 over pi has to be equal to my diameter. Now, cost has to be equal to 100 times 200 over pi. That's the area of the rectangle part, plus pi. And if the diameter is 200 over pi, then the radius is 200 over pi divided by 2, which would be 100 over pi squared. Questions?
For the area of the square, would we still use the pi diameter? Because wouldn't that give us the radius on the outside of the circle? Or not the radius, like the section on the outside of the semicircle?
The diameter, let's see. Area is pi times the radius squared.
Sure, the semicircle makes sense, but for the square, would we still use 200 pi? Because wouldn't that be like a semicircle diameter, not an actual point-to-point diameter for the square?
That's, well, the diameter of the semicircle is the end of the rectangle.
Okay.
So for the area of the rectangle, you need length times width. And
okay. That makes sense. Yeah, okay. I was just confused by the pi, I guess, because I don't see pi's in squares normally.
Yeah, I understand. Yeah. So you would actually plug that in the calculator and get a number with a decimal in it, because nobody has a measuring tape with a pi on it. Okay, we have struggled with those enough. Let's do some solving. So I'll open up my other sheet. And we'll take a couple of those problems that we looked at earlier. We'll differentiate them and set them equal to 0. So our goal here is to practice setting derivatives equal to 0 and solving. Because after figuring out the equations, setting the derivative equal to 0 and solving is the hardest part of the problems. So we're going to take that first distance formula that we worked with. And I had simplified it. So I'm going to write down the simplified version. But I just did some algebra on it. I took what we had and squared and added combined like terms. So we ended up with distance is equal to the square root of x to the 4th minus 4x cubed minus 12x plus 8. Then, of course, when you're going to differentiate, you rewrite it with a rational exponent. And then when you take the derivative, 1/2 falls down, x to the 4th minus 4x cubed minus 12x plus 8. Inside function stays the same. multiply by the derivative of the inside function. And then I usually rewrite it, bringing that negative exponent to the bottom. And then you set that thing equal to 0. Now, recall if you were looking for critical points, you would also need to check when this derivative doesn't exist. So that would happen when the denominator is equal to 0. We're just going to actually look at when the numerator is equal to 0, because that's when the derivative is equal to 0. And the derivative is equal to 0 when 4x cubed minus 12x squared minus 12 is equal to 0, and that does not factor. I plugged it into my polysolve button and got about 1.31. So let's plug it into the old polysolve button. Let's see, 4, negative 12. And okay, this is a cubic. I need to get out and quit and start again. Probably solve my cubic equation for negative 12. Looks like this is the last thing I solved. Nope. 18. And D is negative 12. So I get negative 12, which is, oh, no, this hasn't solved yet. I get 1.31. And then I look at those and I see, they look exactly the same. So I arrow over and I realize that those are both imaginary answers. I don't want the imaginary answers. I want the real answer. So 1.31 is the winner.
Why did you put 18 into it? So you did 4x cubed minus 12x squared plus 18x and then minus 12?
Yeah.
But if you look at your board, that's not what you have on your board to your left.
I lost something, I think. Let's see.
You lost an 18.
I did lose an 18, so let's see. Where did I get 18 from? I made a big fat typo is what I did.
I'm not sure where you got 18 from.
Oh,
right?
2 times 9.
Oh, yeah. Okay. Yeah, that makes sense.
Okay, yeah, that's where I got it from. I wrote down the original thing incorrectly up here. Let's just get rid of that. Okay, it's gone. So let's look at the right one over here. So
that makes
I have
more sense now.
Yeah.
Because I got a completely different answer.
But I think I have it right on the sheet here. Yeah. Okay. Yes, I had just differentiated incorrectly there on my little board.
I think you forgot the 9x squared on the board.
I did. Yeah, you're correct.
That made everything weird.
That made everything wrong.
Yeah.
But another little trick about the distance formula, if you look at the distance formula, you have something sitting underneath the radical, x to the 4th. I'm not even going to write it down. I'm just going to say we have a function over here. This thing has the exact same maxes and mins. As just the thing living underneath the radical. So I could have not even done the chain rule. I could have just looked at the derivative of that radicand, the thing sitting underneath the radical, and set that equal to 0 and gotten the right answer.
Oh, because the radical goes to the denominator anyway.
Exactly.
So that's just the domain restriction.
Yeah.
Okay.
All righty, let's look at the circle one. And I'll write it down correctly this time. So my area is equal to 4x. That was the width of my rectangle. Well, 2x was the width, and then 2 times 100 minus x squared was the height of my rectangle. So this is a product rule, and I write big, so I'm going to turn my board to the side. So maybe I'll have room, and maybe I'll do it right. So we have first times the derivative of second, so 1/2 of 100 minus x squared to the minus 1/2 times the derivative of the inside function, which is minus 2x. Yeah, I still didn't have enough room to write it all in one line. So first times the derivative of second plus second times the derivative of first. Well, that cancels with that, makes life look a little bit better. I'm left with a minus 4x squared sitting on top of the fraction bar, and then a 100 minus x squared on the bottom of the fraction bar, plus 4 times the square root of 100 minus x squared. So I think I made it through all of that. Now I need to set that equal to 0. You have a couple of choices. You could rewrite this as one handy dandy unit and then just set the numerator equal to 0. Or you could add this to each side. You get 4x squared over the square root of 100 minus x squared is equal to 4 times the square root of 100 minus x squared. And that's the same thing as if it were sitting on top of 1, so you could cross multiply. Well, both sides have a 4, so divide by 4. Divide both sides by 4.
I have a question.
Yes.
The equal sign cross multiply, I don't know, I don't remember that. Do you not get rid of the both 100 minus x squared? Cross multiply?
I multiplied them together, and then I had the square root of 100 minus x squared times the square root, just leaves me with 100 minus x squared.
I see. Okay. Okay.
Yeah, it looks a whole lot friendlier after you do that.
Yeah,
which is the whole reason I do it, because it goes from having these ugly square roots to not having ugly square roots.
Well, you're going to end up square rooting it anyway, I guess, at the end.
You are. You're
yeah.
going to end up bringing it back, but it's gone for a brief and shining moment.
Yeah.
So I'll add x squared to each side. So 2x squareds are equal to 100. So x squared is equal to 50. So x is equal to plus or minus the square root of 50. And since we were talking about distance here, we end up with just, okay, what did I lose? Let's see. Four x times 4. I should have ended up with the exact same answer. 4x. Oh, I didn't. I have a mistake here. That should be 400 sitting on top, and then I would have the exact same answer. Okay, so I'll have to fix that one too. I will send you edited versions of these sheets if you want. I always find my mistakes during the morning session, and then in the afternoon section, I'm perfect.
I think I was in your morning session last time too.
Sorry.
That's fine. Everybody makes mistakes. I make mistakes a lot too. So.
Well, yeah, we all do. So yeah, but plus or minus square root of 50. Makes sense? Okay, so yeah, that cross multiplying is a little trick that's going to come in handy. Let's see, differentiate the function that represents the surface area of a box with a square and set it equal to 0 and solve. So let's do that one.
Yeah, I think for the cross multiplying, I was initially thinking like cross cancellation, I guess, where like you have them in the same, but they're not across from the equal sign. They're multiplied together, right?
Yeah, then you could just cancel. Exactly. Yeah, you wanted them to just go away. Well, it's not that good. They don't go away, but at least they look better. They look friendlier. So let's start with just my surface area formula. 2x squared, and I take 100 over x and rewrite it as 100 times x to the minus 1 power. So s primed is equal to 4x minus falls down, subtract 1 from the exponent. So 4x minus 100 over x squared. So you can do the same cross multiplying trick here that we did before. You can make it into one handy dandy unit like I did there, or you can just say this has to be equal to 0. So 4x has to be equal to 100 over x squared. Same thing as 4x over 1. So 100 has to be equal to 4x cubed. So x cubed has to be equal to 100 over 4. And now you're thinking, wow, if only that were x squared, I'd get a really nice friendly answer. But it's not. It's the cube root of 25 is equal to x. That one was easier. And then we'll do the one with the volume of the cylinder. Equals, oops, 75r over 2 minus pi r cubed. So b primed is equal to 75 over 2. Remember, that's just a fraction. You don't have to use the quotient rule on that. Minus 3 pi r squared. And this is the easiest one yet. 3 pi r squared is equal to 75 over 2. So r squared is equal to 75 over 6 pi. So the radius is equal to the square root of 75 over 6 pi. And usually when you're doing your work, you'll want to show your answer like this, and then you'll plug it into your calculator and get an approximation, and then you'll write the sentence that the cylinder with the minimum volume would have a radius of something point something inches. After you do this, you're going to have to check and be sure that it's a minimum, though. Any other questions?
No, I don't think so.
Okay, good. Hopefully it was helpful. Let me put that post survey out here for you. Let's see.